Next, we discuss what happens when a star leaves the main sequence. So, if you recall, a star is on the main sequence as long as it's burning hydrogen in its core. So it leaves the main sequence when it stops burning hydrogen in its core because it's run out. It's exhausted all of that supply. We talked a little bit about this before, but keep in mind hydrostatic equilibrium. If the hydrogen in the core runs out, that means that there's nothing right immediately to push back against gravity, so gravity is going to compress the core. The core is going to collapse a little bit. And as that happens, the helium may become hot enough to burn. So the nuclear fusion of helium will begin. And this process is called a helium flash. That's when the helium first ignites. So we'll have a series of things happening within the star. The star starts to become layered, more so than it was before, by what's happening with the hydrogen and helium. The process that helium undergoes to fuse into heavier elements, namely carbon, is called the triple alpha process. So the triple alpha process will be happening in addition to the proton-proton chain. So at the core of the star is all helium. Outside of the core, there will be some helium fusion happening with the triple alpha process, and then hydrogen will be burning around that, a hydrogen shell fusion. We mentioned that in a previous video, that hydrogen in the shell outside will start burning as well. Now, these different layers are defined by what's there and also what's happening. So at the very center, what's left behind from helium fusion is carbon and oxygen. So there'll be a carbon and oxygen core of the star, and then layers of helium fusion, hydrogen shell fusion, and so on. And so in this layered state, the star is actually pushing its outer envelopes, its outer atmosphere out farther and farther. So it's growing in size, and by that, growing in luminosity. So on the HR diagram, it's left the diagram become more and more luminous in that process. And the helium flashes will cause these bright stages to happen. And there will be some cycling up and down. So it won't just be a continual rise in luminosity. It's growing in luminosity as the helium core flashes, and then that will sort of dim down for a while. It'll lose luminosity, and then the helium shell will flash, and it will rise in luminosity again. So a star like our sun will follow a process like this, where the layers are undergoing fusion at different points in time, and the luminosity is fluctuating up and down, and the size of the star is fluctuating up and down. Now for the sun specifically, the stages are given in this table here. So we can see the main sequence stage, then it becomes a red giant, helium fusion begins, and then it becomes a giant again, and we can see the lifetimes of these things. So approximately 11 billion, I know I said 10 billion before, these are sort of rough estimates, so 10, 11 billion years it's on the main sequence. And then it'll become a red giant, and it'll be in that stage for 1.3 billion years. It'll burn hydrogen for 100 million years, and then be a giant again for another 20 million years. Its temperature is going to change as the size of the star grows and shrinks. It's also heating up and cooling down, and its luminosity is going up and down as well, and the size of the star is going up and down. So the current size, if we call that 1, it will become 165 times bigger when it's a red giant. Then it'll drop down to only 10 times bigger, and then it'll grow even larger to 180 times bigger. And that's the process that the sun will go through as it evolves off of the main sequence. Now, in these giant phases, they're so large that the outer atmospheres of the stars drift off into space. They get pushed away. There's always going to be an equilibrium that the star is moving towards, but as it's growing, those the atoms and molecules in the outer atmosphere might expand a little bit too fast, so when the star contracts, those get left behind and they continue moving out into space. That wave of outer atmosphere that's ejected from the star is called a planetary nebula, and they can look very, very different. So the four images here on this slide are different images of planetary nebula. So they're not stages of a single planetary nebula, they're different planetary nebula. Their colors can vary, their shape can vary, but in general they tend to be sort of round, and that makes them look like planets. They don't actually have anything to do with planets. The name planetary nebula is just descriptive of how they appear, not what they really are. They are the outer atmospheres of the stars that have drifted off when it went through its giant phase. Okay. Now, stars, the nebula around stars can look very different because our perspective on them can be different and because the stars themselves are different. And so, for example, in the diagram here, we can see one. So this is our perspective on the star Eta Carinae. So to the right, this is a Hubble image of it, and this is that image blown up, bigger, right? We see these lobes of gas, and you might not see this directly, but it's sort of indicating that it has a rotation axis. The star is rotating around, and the jets of gas are emanating along the axis of rotation. We can measure how fast these gases are moving, and they're moving very fast, thousands of kilometers per second they're ejecting from the star. But they just appear frozen in time, so we don't see these changes because the star is so far away. Even that rapid motion is not detectable except over longer periods of time. But now when we look at it and look at our perspective on it, so this is indicating our point of view. So this is an eyeball looking at the star, and so we're perpendicular to these lobes of gas. So here's the star at the center. There's a sort of round torus-shaped disk around it, and then there's these lobes of gas that are being spread out into space. Now, if you look at a nebula like this from this perspective, you see the lobes of gas. But if you look along this axis, it will look very different, and now you'll see it more as a round planet-looking thing, like this nebula called the Helix Nebula. So the stars are different, and so their planetary nebula will be different from that reason, but also because our perspective changes, the planetary nebula will look different. Now, if you're interested in these planetary nebulae and how they can appear, there's a short video that I linked to that will show you a lot of the different planetary nebulae and tell you a little bit more about what you're looking at when you see them. Okay, so I focused a lot about stars like the sun to sort of tether us to what we're most familiar with. But the stars much heavier than the sun have slightly more intricate inner workings as they evolve. So a star like the sun we consider a low mass star. So it's a lower mass star than how they can become. Stars can be much, much more massive than the sun. So we put the sun in the low mass category. Those types of stars will burn their hydrogen, they'll burn helium, and then some of them might even be able to keep going and convert carbon into heavier elements, do carbon fusion, essentially. Now, the sun will only burn hydrogen and helium, but other low mass stars might get into burning carbon. But that's about it. For heavier stars, for higher mass stars, they can, not surprisingly, burn heavier fuel. So when the sun gets to a carbon core, it doesn't have enough internal pressure to burn carbon. So it gets sort of stuck there. We'll talk about what happens with the sun when it's stuck there later. But for now, it gets stuck there. For a heavier star, a more massive star, it can burn the carbon. And not only can it burn the carbon, it might be able to continue burning oxygen and then magnesium, neon, silicon. All of those heavier elements can get burned until it gets up to iron. So the key for high mass stars is they can burn any nuclear fuel up to a size of iron. And that's because when you squish iron together, it doesn't actually release any energy. So we talked a little bit about the way fusion differs from fission when we first introduced the ideas talking about the sun. Fusion works for the small elements, combining them together to make bigger elements. And if you combine two elements together, it will produce energy. Well, if you go to the other end and take a really big element and you split it up, it can also produce energy. So for light elements, you fuse them together to make energy. For heavy elements, you split them apart to make energy. And that means there's going to be a point in the middle where you can do neither. And that point is iron. So elements that are smaller than iron can be fused. Elements heavier than iron can be fissioned. But iron can't do anything to produce energy. So if you're a high mass star and you're continually going through these compressions and contractions, evolving off of the main sequence, becoming layered with different types of elements, eventually you reach iron. You've produced iron through fusion. And you can't burn that. And so the fusion will stop at that point. There's nowhere to go from there. Or I should say there's no more fusion processes that can happen just from the pressure of gravity squeezing on the star. So you can't just bypass iron and then start fissioning, because fission doesn't work in the same way. You need to split apart an atom, not fuse it together, and the pressure would only fuse them together. Okay, so just to recap, for a low mass star, it gets stuck when it gets to around a carbon core. And for a high mass star, it gets stuck when it gets to an iron core. Now what happens to them from there can be very, very different. And so in the next video, we'll get into how stars eventually die. What happens to them once they reach this stage where they can't burn nuclear fuel in their cores any longer.